I am pleased to introduce Brandon Mitchell. Brandon is one of our esteemed Docker captains, and today in this session he is going to share the top tips and tricks of the Docker captain. So Brandon, go ahead and take it away.
Thank you. All right. So this talk originally, thank you. This talk originally was started by another fellow captain named Adrian last year. He is unfortunately away on a honeymoon, so I get to take over for him. So I'm going to fly through these slides pretty quick. If you're a picture taker kind of person, go find my GitHub page. The GitHub page has all the slides in there already. You don't have to take a whole bunch of pictures because you're going to miss them every chance you get. And that's because I've got about 8 different bullet points I'm going to hit. And when I hit these 8 different bullet points, we're talking 40 minutes. That's about 5 minutes, so we're going to go through quick. GitHub. Look on the very bottom of the slides. There's a little sudo bimount down there. Same thing for GitHub. It's just an underscore dash. Swap that thing. I'll even give you this slide here. All right, so who am I? I am a Docker captain, Brandon Mitchell. You heard that part. Bimount, you'll see that handle some places on like the Slacks and other places like that. The solutions architect, that's my job title. So solutions architect for BoxBoat. We are a Docker business partner. I see people in the background over there saying, yes, tell them more, all this good stuff. That's my mandatory plug, so they approve my expense report. All right. Docker captains, we are basically, you can think of it as kind of a community-based evangelist program. Docker sees people are out here giving talks, doing blog posts, all that other good stuff. And they just promote us to a job title, give us a whole lot more duties to do, and with absolutely zero pay because we're not employees. They saw me after I frequented way too many Stack Overflow posts, answered a lot of questions over there, and so that was kind of my adoption into the program. So, enough about me. Who here is a developer? Show of hands. A whole bunch of you. Holy cow. I'm outnumbered. I came over here from the ops side. Don't tell anybody. Some of these tips I'm going to give you are a little bit ops focused, but I promise they do apply to the developers as well, so don't panic. So the first thing the ops people want to solve on their side is a full disk. But I'm sure a couple people have seen that on developer machine too. So the full disk, Docker gave us this solution a while back, Docker system prune command. You run this, does exactly what it tells you it's going to do. It's going to delete those containers that are down. Sometimes you might not want to do that, so be aware. If you delete something in production, that would be bad. It's also not going to delete a few other things that it tells you that it's not going to delete because it's not on the list. Things like the running containers. So if you have a container that's been up to 3 months, it's not going to clean that up. If it's a tagged image, it's not going to delete that by default, or volume, stuff like that. So you can have a lot of data out there that's not getting cleaned up for you. So be aware of that. But otherwise, it's going to automatically clean this stuff up that it does tell you that it's going to do. If you want to automate this, Brett Fisher had a cool tip a while back, another fellow Docker captain. And what he put out there was this little while loop that's running inside of a container that he kicks off. That container is running the Docker image, so it's got the Docker command line in it. He mounts a Docker socket, so he has access to the host that way. Every hour, this thing just automatically deletes anything that's not running, anything it can clean up. So, pretty quick way to accidentally delete some data you didn't want to accidentally delete, but it's a good solution. If you want to accidentally delete data across an entire Swarm cluster, I got good news for you. You can do that too. Just the mode global, change that. The mount, instead of a volume command, I had to split the mount across 2 lines here, but that is just one long argument. Different syntax for the volume mount, same thing we're running inside the container. So good. We just accidentally deleted data across an entire Swarm cluster. We no longer have full hard drives. Let's talk about the other thing we couldn't clean up, and that was logs. Because those containers, when they're long running, they're kicking off and they're spewing out a whole lot of logs, they can fill the hard drive up. Let me give you an example of this. On the top of the screen, I've got a container just spews out a whole lot of logs. Hopefully you can see in the back because I can't change the size on this. In the middle, I've got just the internals from Docker where you can see the file that Docker is writing. So that file there is written in a JSON format, and it's just going to grow and grow and grow. And on the bottom, what you can see is the amount of logs that are actually being written into that. The JSON adds some overhead, so we get to see some of that here. All right, so this would just go forever. We can change it though. By default, it's unlimited. But if we pass a couple options here, and the first option I'm passing is a max size as a log option. Second one is a max file. We pass these options, Docker will internally just do an automatic log file rotation for us. So we can get this rotation happening under the covers, just automatically. And I can let this run for a long while, and you will just see these things going and going and going. It will make one file that's 10 megs. Once it fills that up, it will make another file that's 10 megs. And it will keep rotating. Once it hits that third file, it's just going to delete the oldest file, make a new one. So you get between 20 and 30 megs of logs. That size is the size of the JSON file. It's not the size of your actual logs themselves, it's the size of the JSON on the disk. So you know you're not going to exceed something, but you're going to have a lot less in your application logs, because JSON's adding, from what I've seen, about 50% overhead in this. All right, we can make this even better. We can go through, same example, but I added a new log driver option in here that says change it to a local log driver. This came out just in 1809. The default we've had before this has been JSON, so that's got about 50% overhead. It puts its logs in a different directory. So I got local logs here. That's a different place that it puts it under the container. Docker really don't want you to know too much about that. They want you to just take it on faith that they're storing it somewhere safe. Before everybody was looking directly at the JSON logs, it made it very difficult for them to change things. So if you don't look at that, that makes their lives easier. It stores it in a different template. It's storing it in a protobuf instead of JSON. It's got less overhead. If you've got something that is parsing these logs directly, back in the day, there were a lot of log forwarders for stuff like Splunk and Elastic that was parsing that JSON log file. It's not going to work with this. But otherwise, this is going to give you a lot less overhead, so you're going to be able to pack a lot more of your logs in that same 10 megs. And if you just looked, we compressed that log as soon as we rotate it. So now we're taking up less disk space to store more logs. So we get double win here out of this. So this just came 1809. New way you can store your logs there. All right. So if we're running this, this is a whole lot of one-off Docker run commands. Let's do this in Compose, because I think a few people out here might still be using Compose, right? So we got Compose. You can pass all these same options there. Same fields, just a little bit different syntax. If you want to eliminate some repetition, because a lot of us have more than one service in a Compose file, here's a nice way to start eliminating some repetition in your Compose files. This applies more than just to logs. This applies to any Compose file out there almost, except this first highlighted line. Other than that, all this stuff applies to all Compose files. The first line, x dash, is an extension field that Docker gave us. Anything that begins with an x dash, you put whatever you want in there. As long as it's a valid YAML syntax, it's yours to put whatever data you want in there. This is a user extension field. You need at least 3.4 of the Docker Compose file to use this. Inside of that, I've just made a couple sections in there for the default values for some services I'm going to run. So these default values, I'm going to use them by using a anchor syntax. That's the ampersand default service in there. Anytime you put an ampersand in front of something, that defines an anchor inside of YAML. An anchor, you can think of it as defining a variable. And down below, I did a star default service. That's using that variable. And when I use that variable, that would normally just override all the settings for cat. I want to merge this together, so I have the double left arrows there that says merge that one value with all these other values, and now I get a combination of those for my service that I want to run. So what this gives us the ability to eliminate a lot of duplication we have in our Compose files. But not just that, those last few things, the anchor and the alias and the merge, that's all normal YAML syntax. You could use those in all your Kubernetes files as well. So you can start eliminating some of the repetition, define a value one place, and you don't have to change it 12 different places every time you change one thing. So that can save you a lot of issues in there. I don't use any of this for logging. For the logging, what I do in Docker is I change the daemon JSON file. When you change the daemon JSON file with these fields, this changes the default for every container created on that node from this point forward. So you change this one setting one place, and now every single container from now until whenever this engine is gone are going to have these as a default. You can always override the default. You can change the setting if you need to, but you get this going forward. It doesn't change any containers that have already been started and running. So if you have a disk that's already about to fill up and you try to change this after the fact, those containers already have the old settings from when they started up. All right, so I promised the developers in the room, and there are a few of you, this was not just a Linux server talk. If you're on Mac, you can do this on Mac. Anytime I talk about the daemon JSON file, you can go into the daemons tab in there, go over to advanced, and you can change all these settings just like you would on a Linux machine. Got the same box here. They even improve it. They give you a nice little JSON syntax verifier. It tells you if you type something wrong. Windows users, I didn't forget about you. Same field, same box. So anytime I start giving these tips and they look very Linux heavy, they apply to the desktop just as well. So we can avoid filling up our desktop hard drives. All right, so I just automated myself out of a job. Nobody has any more filling up hard drives. So now let's talk about who's recruiting in here, because I might need to be looking later on. I'm kidding, my boss is back there. He's going to strangle me later on. All right, let's talk a different kind of networking. Let's talk subnet collisions. And the subnet collisions I'm thinking about is when you create a network in Docker, Docker usually sets up the IP networking for you out of the box, under the covers, with some default settings. it looks for what subnets it can see, and if it can't see you using that subnet anywhere, it'll just start picking it if it's one of these private subnets. So you'll see these 172 networks, stuff like that going on under the covers from Docker. It just notices you don't have a route to that right now, so it can use it. That works great if you have a server, but if you have a laptop and you go from the office to the coffee shop to home and connect to the VPN somewhere else, at some point you'll invariably have some collision where you're using the same subnet that Docker network started using. We have a fix for that. The first one comes way back in the day. It's an old fix called BIP. This stands for the bridge IP. And what this fixes is the IP used by the default bridge named bridge. This is for any container you spin up that you don't define a network for. So anything that you just say Docker container run and you don't specify a network, it uses this bridge. We've got another one though that had to come out later on because a lot of us create networks for our containers. A lot of us do use Docker Compose to spin stuff up, and you have other bridge networks you're creating. What we had in 1806 is a default address pool. And that default address pool, you define what subnets you're allowed to use for any containers that Docker can pick from. You define the large pools, and you define how big Docker can pick from these pools. So the /16 says, give me a couple Class B networks that Docker is allowed to pick from. And the 24 says it's allowed to pick out some Class C subnets out of that whenever it creates a new network. These are for bridge networks. So this, if you say Docker network create, if you say Docker compose up, this is going to apply for the bridge networks. We still need for the swarm users. I think there are a few swarm users in the room, hopefully, right? Give me a cheer. Come on, somebody. All right, we still got a few swarm users. We got a fix for you too. This came in 1809. And you need to do it for when swarm does a swarm init. So you have to do this early on, and you can specify the default address pool, same syntax we had on from the previous screen, and a default size, how big it can pick from those pools. This is CIDR notation, so these are blocks, the bit sizes, how much of a net mask it can pick from there. So same options. Now we no longer have networks colliding as long as you figure out what the coffee shop uses, what your VPN uses, what your home uses, and find something that's not being used by anybody else. You can pick a network there. Works great until you go to Barcelona and they decide to make the network over there a 172 network and break every single person's Docker install. It was fantastic. All right, so we solved the network collisions. Let's go on to some other network debugging challenges. And the challenge I face a lot of times when I'm debugging networks in Docker is I'm looking at something that's running inside of a container and I want to know what's happening in that container, but I don't have all my networking tools in there. You go into the container, you do like a Docker exec in the container, and you found out you don't have an NS lookup or you don't have a ping command or something like that, and you could try to install it, but that's changing the container. What if you have some read-only containers? What if you're not root? All these different challenges. I got good news for you, and that is that Kubernetes has all their sidecars and Docker has them too. Docker had sidecars from before even Kubernetes did. What this looks like is if we spin up a container and we say make an Nginx container here, I'm going to call this container web. And I'm going to publish a port 9999. Going to kick that one off. Down below what you see is I say the network is a container colon and the name or an ID of another container. When you do that, these two containers are running in the same network namespace. So I'm running an SS command here that's the same as like a netstat, and you can see port 80 from the Nginx container. They're listening, so we can debug that network as if we're in the same machine because we are. We're in the same network namespace. We have our own file system with all our own tools. That's the net chute that we've got all the tools with, but we can debug it. Second example here, I'm just doing a TCP dump. So TCP dump on port 80, I can look at this traffic when it's inside the container, and I don't have to install any of this stuff inside of my Nginx container. And there you can see all the traffic going by, all the requests going through. So we can debug to see, did the request actually make it all the way to the container? If it did, what did it respond to? We can start debugging this stuff from within the container namespace. Because otherwise we're trying to run tools on the host and they don't see it from the network namespace of the container. Or otherwise we're trying to install tools inside of our image, and that's going to upset the production people because they don't want us throwing all these tools in there. They wanted this nice, slim, isolated container that doesn't have all these things in there. All right? So in case you missed that one, --net, and it's container colon and the name or the ID of the container, and you can be in the namespace of another container, just like that. All right, and I use this ping, curl, NSLOOKUP, all kinds of tools. Nicola Kabar, I believe is how you say his name, Docker employee, or at least he was. I haven't kept track of him. He made this netshoot container out there that has all kinds of network troubleshooting tools. You look at his GitHub page, there's all kinds of fun stuff in there. Check it out. All right. Layered file systems. I want to start covering this one because for a lot of people, layered file systems are a black box. They see it as very ambiguous. They hear these things. And what they'll see is someone tells them, hey, you know what? Let's take an example container here and let's try to figure out what's going on. So I'm going to call this my bad Docker file because it does everything wrong. We have all these run commands separate out. We do all these things the not right way. It is built on Golang. And for all my demonstrations, I do my build with a nice fully populated cache so that it takes a split second to run. And I'm going to look at the Golang base image that I used, and I'm going to compare that to the image that we just built. And what I'm looking at is the rootfs layers in each one of these. And this is a whole bunch of SHA-256 checksums, but more importantly, if you look at the one from Golang, you see the FB at the top going down to 3C. And if you look at the image we just built, it's got the same layers in there, the identical layers. What you need to know is that we're not copying anything. We just have pointers pointing to the same thing. And all we do is we extend it with all these other layers. So whenever you make a change, whenever you make a new Docker build, all you're doing is extending. You're not modifying the existing image. You're just extending it with other layers. But this is still, I think, a lot of people glazed over eyes for good reason. This is still a little bit difficult to understand. Let's take it to the next step. Let's do a Docker image history command here. Docker image history is going to give us an output that shows the created time, the command, and the size, and you read it kind of bottom up. So the bottom section here is going to tell us this is our Debian section. This is a base image that we picked from. This is actually the grandparent base image. We built this off of a Debian base image. So you can see those layers. Keep going up, and you can start seeing some layers for the Golang. So we can see all these steps kicking off. So we get a feeling for what's running inside of our container, what's being constructed inside of our image. But now we start seeing the layers we added. And the thing I want to look at is that go build step. That's like 48 megs. Be interesting to see what's going on in there. Why is that 48 megs? We just built a little static binary. We see a chmod and a chown command. That's just changing a small bit, but that was a whole 9 megs, and the RM is 0. Well, if we did a deletion of a file, shouldn't that be negative? So what's going on in there? What's happening to these layers? Why are they different sizes? Let's take this a step deeper. Let's go a little bit farther. To do that, the command I'm going to run is a Docker image build, and I'm going to pass it a couple flags. The no cache just says I want to build this thing all the way over again from the beginning. I don't want to see any cache stuff because that's going to defeat the purpose of what I'm getting ready to do next. The next thing I'm running is an rm equals false, -- rm equals false. When you pass this, all those intermediate containers that Docker runs, when it does its build command, every time you do a run command inside of that Docker file, it uses a little temporary container that kicks off the command, and it looks at the result of that. Normally it deletes those temporary containers because you don't want to clutter up your system. We're going to keep them around for a second. And the reason I'm keeping them around is I'm running a Docker container diff command afterwards. Docker container diff is going to tell us what's different from this container from the image that it was spawned from. And when you're doing a build, that image it was spawned from is just the previous state of the image. So here's what I'm running. The rm false and the no cache option. I've already done this build because it takes longer when you don't cache anything. And I run this ls command. I'll clean up that screen here in a second. It just has a hard time when I type these long lines. What I'm going to look at is what's going on under the covers with this go build command. And so I'm going to run this Docker container diff on the container ID for the go build command. And when I run that, I'm going to see a whole lot of just cache lines. A whole lot of lines of all the Go cache that's being run from the Go mod, and then later on you'll see the Go cache. In the left-hand column, you see an A character. The A character means this file did not exist in my parent image. I added this file. This is a new file for this image that we just created. This container we're running right now, this is a new file that's getting ready to be added to that layer. And the very end of this, when I get down the bottom, you're going to see one little file there coming up. There it is, source app. That was the only thing we cared about, but we had all this other cache in there. So now we know what we want to clean up when we start building our images to make them more efficient. Next one I want to look at is that chmod and chown. So let me pick on that chown command. Because we saw that chown, that's just flipping a small bit, permission bit inside of Linux to say change the owner of this file. Change it from being owned by root to being owned by our app user. But that little bit flip there costs us 9 megs. And the reason is because we're doing a copy on write. That's the C. Every time you change a file, the entire file gets copied. Make a small change to a big file, you get a big change. Lastly, what I want to look at is the rm command here. And the rm command is telling us that we deleted something, we see the D. So we see that we deleted something. That only gets applied when we assemble all these layers together. Before that, that file still exists on the previous layer. So when you start pushing and pulling stuff up to the network, over to a registry, something like that, on the disk locally, all those files that you just deleted are still there. So you haven't deleted them at all. It's just when you assemble all these layers with the overlay file system that Docker uses under the covers, that's when it says register this file, this directory is being removed, and so a container can't see it, but that file is still on the disk. And so this is why I call this image the bad image. The way we fix this, the way we've worked around this from as far as I've ever seen Docker, is we delete the temporary file in the same step that it was created in. So if you have a process like a Go build and it's creating all these cache files and you don't want those to get included inside of your image layers, you have to delete that in the same step. And similarly, if you have some small changes, chmod, chown, you change a file, you need to make that change in the same step when that file is created to eliminate it. How do we do that? It's chain the run commands. We take the bad Docker file that has all these run commands separated and make it the good Docker file that has them all chained together. And this is probably, if you've ever gone out and looked at a Docker file online, you've seen a lot of this. And that's why they're doing it. They're getting the files modified in the same stage where they create them. That eliminates any changes getting copied on write, getting added to another layer. All right. The downside is that this is going to build slower. We're not going to use the cache as much. You change one line, this you got to rebuild that entire step. So what Docker came up with not a little while ago was multi-stage builds. This changed everything we learned a minute ago, just changes it, flips it on its head, says unlearn everything you've figured out. Because what we do is we start building our build stage in the beginning, and then we say, just copy that one file we wanted out of that stage to the next stage. Let's see an example. It's easier to see one example. What we have here is the Golang base image up top, and that's our build stage. That has all the tools that we need to build our environment, all the different components we're running, and we can create our app. When we use the next stage down below, our release stage, we say copy just that one file from the previous stage to the current stage. So we're changing this, entirely, flipping it upside down. The important part is we don't have to do any cleaning up of all of our Go mod cache, any of that stuff, because we don't ship that. We're not pushing that to a registry. We just tag the one stage that has the release image. The nice part about the multi-stage to me is that for anybody that's doing a CI/CD workflow, you've got the build servers, you've got the Jenkins admins out there. The operations team has to keep installing new versions of Java for you, upgrading the Maven, all that stuff. Developers now have control in this environment. Developers say, I want this base image that can build this environment of mine, and they can change and pick and choose what they want to use, and all you have to do from the ops side is just give them a Docker environment, and they say Docker build, and they're up and running. All right, so what does this look like? Real quick. I'm going to take this build command for the multi-stage build, and I kick it off. Again, I cache everything because I like these demos to go fast. And just to prove that what I built was what I was just showing you on the previous screen, there's the same Docker file. And if I look at the resulting images here, I'm going to see that I went from 833 megs down to just 9 megs. So we just extremely shrunk down this image. And the reason is because that Scratch image that I based it off of, Scratch in the Docker land, you can think of it as an rm-rf on slash. There's nothing there. There's no shells, there's no libraries, there's nothing. For the Windows people in the room, that's a format C. You just gave it a completely empty file system. And sorry, this slide is getting a little hard on the wrapping there, but you can see if you look at the history, there is no parent to this image. Everything here was just built at the same time. All right, so that fixed everything. Everybody started making their move to multi-stage. If you have something like a Java environment, you say you can't use this, you've got a JDK that you're building off of, you can go to a JRE. You're still shrinking this environment down, you're still making a minimal runtime. So whatever you need to run your environment, you can minimize it. And that's what multi-stage gives us. But we can do better than that. And that's where BuildKit came along. BuildKit said, that was cool, let's have some fun here. So they came up with some features that are really nice. They're good for everybody. It doesn't matter whether or not you use all the cool experimental stuff. You can take your existing Docker file, put it in there, use BuildKit. And some of the fun stuff it does comes around the context. Whenever you do a Docker build command, that last little dot at the end of the command line, that says take this current directory I'm in, package it up, ship it to the Docker server, and every time you say a copy or an add, it copies from that directory. Well, if you're in a very large directory, that packaging and shipping it over can take a while. If you have a huge source code repo, that can take a while to ship that over to the build server. Even if it's the same local machine, it's still doing an internal package and send it over. BuildKit does away with that. First thing they do is they say, only copy over the stuff that we explicitly copy or add. Nothing else in there. So anybody that's been doing a lot of Docker ignore files, excluding all kinds of stuff in your repo, you don't have to worry about that anymore. But the better part about this one is it looks at what we ran last time. The last build we ran, look at the context from before, and do effectively our sync command. Only copy over the changes. If you have a source code repo that's got 200 files in there and you change 3 of them, this is only going to copy 3 files when it does the next build. So your next build is a little bit faster to start. It also does some stuff with the multi-stage environment where it looks at a dependency graph. If you look at the last slide there, and you might have seen it, I had a dev image down there below. Because the developers might want a shell, they might want some other commands they can work with. That dev image, we didn't use it in production. But when you build this with BuildKit, it's going to see they didn't actually use it. I don't need to build it. It's going to skip that step entirely. That's good if you have all kinds of different environments in there. You can skip over them. It is bad if you have environments intentionally injected in there for something like a unit test or a security scan. You'll have to explicitly build that specific target. So whenever you say a Docker build, you can always specify a -- target and say what you want to build. So it's different behavior, but it's being more efficient. It's trying to be faster. All right. Pruning, I need to show you the pruning part, because the pruning is where it gets really interesting. This gives you a completely different way to prune compared to when we do a Docker system prune. Normally, you do a Docker system prune, you say just clean up all the images, and it cleans everything up, and then you have no build cache at all to start with. This prune, we can pass some flags in here, and the flags we're passing, the until, we say, how long has it been unused? How long have we had this layer that hasn't been used in our environment at all? Let's go ahead and clean everything up that is older than that. And I also passed a keep environment, a storage thing, saying keep at least this many gigs of files. So now our build server, we can have this setting on there. We can run this command and clean up all that stuff. It's going to keep at least a couple days and 1 gig of files. So we don't delete our entire cache, just the old stuff we're not using recently. All right? If you like that much, we can automate this. I love automation. Operations loves automation. It means less time for us to do any work. That automation looks like a little daemon JSON file entry. And this one, you're not going to find the Docker documentation yet. I'm sure there's a Docker person back there in the room saying, crap, we need to submit a PR on this one. But they've got this policy out there where you say GC, that's garbage collection, and you can define one or more policies. Every time a build completes using BuildKit, it will run this policy for you. So it'll automatically clean our environment up. So if you have a build server that's normally filling itself up on the hard drive, this is how you solve that. Just that easy. All right. So once you make the change to BuildKit, the next thing that the developers are going to want to do, because developers like to be cool, is they want to play around with the experimental features. And Docker has some good ones. They changed the parser using an image. That's kind of an interesting way of doing it. They have an image out there that parses the Docker file, and they put the experimental features in there. If you want to implement your own, you can build your own parser. If Docker changes their experimental features and you want to keep the old ones, you can always grab their image and say, depend on my version, not their version. So that's kind of interesting. They have everything else in the current experimental features are different mount commands. So when you run a run command in Docker, you can specify in here a -- mount, and then they have different types. And the different types gives you ways you can mount different volumes in that temporary container that Docker is running that tells you that you can inject some data in there that doesn't get written to the image, doesn't get written to that file system. So why would you want to do that? I'm going to take the first example here, the bimount. In that example, I'm thinking of something like Aqua's microscanner. Not sure if anyone's ever heard of that. They run a scanner that runs inside of the container during the build process. If we injected that, we could say, do a bimount from another image that has their microscanner in it. That would make that available within a path inside of our container when we're running it. You can now run your scan, and when this run step completes, that microscanner was never installed in our image. It was never written to the file system on our environment. So we can run this stuff, some security scans, stuff like that, without installing tools inside of our image that would bloat our image layers. Kind of a cool trick. The one I really like, though, we got a lot of developers room, probably a handful of Java developers. I've seen the cache option here that is extremely handy. Think of cache as something like the Maven M2 directory. You got a whole bunch of things you've downloaded before. You do another build. If you blow your cache in Docker, normally you download all those things all over again. That takes a long time to download. We don't want that. That Golang image I was just building, all those things, that's all cache. What we really want is to say, make that not part of our image, but mount this into our build, and then the next time we run the same build or a similar build, maybe with 1 or 2 different dependencies changed in there, mount this same cache in there so we can use the stuff we've already downloaded the last time and just download the 2 new files we have. We can speed our build up that way. The next one in there that people are asking for a whole lot is the secrets. The secrets gives us a way to put SSH credentials, AWS tokens, things like that, that can access private resources of ours. Maybe you have a private GitHub server or a private Bitbucket or something like that, and you want to have SSH access. Even if your SSH key is password protected, they have a way to do a SSH agent that you can unlock the key first and inject that during your build. This injects it as a file that's available that it can work with. but it doesn't write it into a layer on that image as you're building it. It never gets injected into your image that you're shipping. So that's the way we can do this securely. So people have been looking for this for a long while. What it looks like is, I mentioned their experimental features get injected as another image. You define that in the top line there. So I'm just using their experimental syntax on the top line. So I switched that. And the run command, I told you it was a -- mount option. And so what I'm mounting here are the Go cache directories. So I'm running that same Go build that I was doing a minute ago. When I do this, let's take an example here and look at it. What we're going to see is up top a classic multi-stage build, so without BuildKit turned on. And I've got one that I've already run there, so I've already cached these lines. What you can see at the bottom of this is I've set BuildKit to be 0, docker_BuildKit to be 0. That you don't have to do, but that's if you want to disable it. If you have an environment where it's been turned on automatically, you can disable it on a one-off basis. So I'm in a second here going to rebuild this image. Down below, I've got a BuildKit version of this, and I've turned on the progress to show a whole lot of verbose output here. So we can see all the output of every step that it's running. So I've already done this before. I've already run this build initially. But what I want to see is what happens when we start changing stuff when we cache it. So BuildKit on the bottom, I'm going to change one module. I'm going to change one version number in here. When I change this version, that's going to have one new dependency in there. So now normally when we change any one dependency, we now have to pull all our dependencies again, and we'll see it on the top. But on the bottom, we've already got this mounted in as the cache. So when you get down to that step, you're going to see right there extracting. It didn't download, it just extracted it. It already had it on the local file system. So if we have a whole lot of dependencies, if you have a big project and you're downloading all these dependencies and you start using these features, you can shrink your build time down even when you're changing some of these dependencies of your application. So this is making things quicker, which is what you want. All right, so if you want to try this out real easily, docker BuildKit equals 1. You specify that environment variable, and now every build that going forward in this shell, so just in this one shell, is going to have BuildKit enabled. And you just run docker build commands like you always did. You need 1809 of Docker, so current stable version, but you can turn this on. If you like it so much you want to make it your new default, you can specify in the daemon.json file. I'm getting used to telling you all these features in the daemon.json file, right? Change a feature flag that says BuildKit is true. And now every build by default, without you changing anything in your shell, is going to have BuildKit turn on by default. So nice, easy way to do it. All right, let's talk about volumes. For volumes, the first thing I want to chat about is if you go looking back in Docker's documentation, and for the people that can't read this in the back, don't worry, the next slide has everything here that's important about it. I'm showing you how to do an NFS mount in a volume using a local volume driver. I think a lot of people in the expo hall are probably upset about this right now because they're trying to sell you all these volume storage tools out there that you can use. They've got NFS out of Docker from the beginning days, as early as you can go back. And you just pass these options. There's a bunch of long options in there. But if we go to compose, the thing I like about this is we go into swarm mode in compose, and we have a container that's running on one machine, and we spin it up, and it has to migrate to another machine, and it has persistent data. Now that persistent data is available to it when it gets to the next machine after it migrates. Now we have an HA service in Docker that's migrating from one node to another that has persistent data, just using NFS. So we didn't do anything fancy. We didn't get all the storage vendors excited with their big payday, but you can do this out of the box. If you're in something like Amazon, EFS is NFS. So you've already got this in most of the cloud vendors out there already. All right, so this is NFS. The local volume driver in Docker is just doing this as a pass-through straight to the mount sys call. So we can do other things. We can mount an ext4 file system. If you have a big block device, you want to mount that directly into your container, you can do that. Mount this directly in your container as a volume, and wherever the container spins up, it just mounts that. All right? I don't see it a whole lot for block devices, but one request I have thought would be interesting to see is overlay. A lot of people know overlay is the image file system, right? You assemble all these image layers together. That's what it's using under the covers. There's an overlay type for the file system type to assemble these layers together. That O option, I had to break it across multiple lines, but that's where all the magic is happening. So that's really one long line there. I just couldn't fit it on the slide in one long line. The lower directories, think of them as your image layers. These are your read-only layers of the file system. And the upper dir are your read-write layer, is your read-write, I can say this, is your read-write layer. That read-write layer is, think of it as your container file system. Whenever you're in a container, you change something, you don't see it in any other container, that's because they put it in its own little spot. in the file system. Work directory just needs to be a temporary directory that's empty, and that's just for the overlay file system to do its magic. So why on earth would I ever think about doing this? My use case I can think of is if you have a CI workflow that has a huge data set and you want to run multiple concurrent pipelines and you want them to have write access to that data so they can do whatever they're modifying and testing and changing in their code, you can have each one with its own private upper in here. It does all of its writes, it sees all of its changes, and you didn't have to copy that data 10 times. You just use the same overlay file system, just like Docker is using, but you're using it for a volume, not for the image itself. So we can do all these cool tricks out here. I'm enjoying this fun stuff. The next one, hopefully you are too. The next one is a bimount. Now usually with bimount, people think of it as the very last line on this slide, the /code and you mount a code. So this is the developer workflow. They mount the code directly into the container and they can try stuff out. The bimount's doing this a little bit differently. It's making a name volume, but it's doing the same bimount. It's the same end result, but you get a couple different features out of this. One is the directory. So I pass that directory. I'm no longer stuck within the var-lib docker volumes directory when you do a normal name volume. Now you can put this in any directory you want to. But the nice part about using a name volume, in addition to putting it in any directory you want to, is that Docker initializes name volumes for you. Docker will look at what's in the image, copy it over the name volume if it's empty, and now you got it pre-populated. What this gives us the ability for someone that gets an image that they haven't already cloned the repo, they can pull that image down and now they can export data from the image to the local file system, work with it, play with it, try things out, and now they've got that directly mounted into the container. They can work with it. So it's an interesting workflow if you want to go the other direction. But most developers aren't doing this. Most developers have already pulled their code out. They've already cloned the GitHub repo, and they want a faster build environment. They want to try things out, they want to make changes, and they don't want to have to keep rebuilding this image every single time. So they mount their code directly into their container, they try things out, restart the container, see it work. So if you're doing that, please, please, please quote that path when you do that, because when you give this to your neighbor and your neighbor has to put spaces in their path, they're going to break this command if you don't quote it. So that's my little quick PSA, a little request for the crowd here. All right, so let's take an example of what they're going to play with. Let's take a Docker file for Java. I'm going to install Maven. I'm going to have the JDK up top in the build environment. And I'm going to run a Maven build, and I've got my Java jar at the end of this. Now, one nice thing here, I also do a user add, and so I'm going to run this as the app user because evil ops people, the security team says don't run stuff as root. And they're right. We shouldn't be running stuff as root. So we've done that. The developer wants to use this, but they don't want to keep building it every single time, so they come up with this crazy Docker compose file that has a whole bunch of different steps in here. One of them I've highlighted is the target. We can say build a specific step out of that stage, out of that Docker file. And so we said build the target stage, not the release stage. So now we have the full JDK to work with. We don't have just the JRE. The command I'm running is instead of just running a Java, I run a Maven build and then I kick off the Java command. So now I'm starting up my application. And I've also mounted the M2 directory in there. So now I have some persistence with that M2 directory. So now my cache is being persisted between different runs. And I'm mounting my code directly in. So now all the developer has to do is restart their container. They're going to rebuild the latest code, and they're going to see those changes immediately. So they're increasing the velocity of their workflow. They're happy. And as soon as they run this, they see a permission denied. How many people have ever seen a permission denied on something like this, right? Yeah, I see a few hands out there. All right. The reason they're seeing that is because the user on their laptop is not the same as that user we just created in the image. It's got a different user ID between the two. Now, I will say the Mac users in the room, most of you didn't raise your hand because Mac's got a cool functionality in there. It's called OSXFS under the covers, if I'm saying it right. It's added in a more recent version. And it handles this automatically for us. It sees that you've got one user ID on the host, one user ID in the container. It does some interesting mapping. It's some cool little trickery going on under the covers. But for the Windows users, the Linux users, you've seen this before. If you mount the Docker socket, you've seen this before. We can work around this. So we got a lot of solutions to this. And sorry, there's a typo over here. There are a lot of bad solutions to this. You can run everything as root. Or you can change everything to be 777 on the permissions, let anybody in the world write to it. If you do that, you will get a visit from your security department. That is not the DevSecOps you are looking for. All right. We can try to make everything to have the same UID and the GID for every developer in the room. I know nobody can keep the same haircut or the same stickers on a laptop. There is no hope in the world we're going to get the same UID on every single developer laptop. We can try to make the UID, we can try to make our images build with the UID of the developers. That means we have to build an image per developer. That has way too many images. Or we can make the UID and GID change when we run our image. But if we do that, any file that was created inside of the image that we didn't mount a volume over top of has the wrong UID, and so now we can't access the files already in the image. So we got a lot of bad options. So the sysadmin here, the ops guy shows up and he says, we can use a shell script. And I got bad news for you. This may not be appropriate for the developers in the room. It is not pretty. Developers don't like shell scripts. What I'm looking at is something like this. I've got an old UID that's inside of my container. This is the ID of that app user that we just created inside of the container. I've got the new UID. This is the ID of the developer on their laptop that we're seeing from the volume mount. So I'm looking at that volume mount that someone injected in there, and I'm getting that ID. If those two don't match, I'm going to change it. And I'm going to change that by running this script as part of my entry point whenever the container starts up. So I'm going to use a usermod command. I'm going to change that ID inside the container to match whatever the developer is running on their laptop. So this container can be a little dynamic. It automatically adjusts itself. And that find command at the end just says, in case usermod didn't automatically fix these permissions for me, any file that was inside the image that has the old UID, let's just fix that real quick. So I've got this script out there. You don't have to memorize it. It's already out on a GitHub repo. I copy that in with this copy -- from option, where I say grab this file from another image that's already out there. That image has a whole bunch of little utilities I like. I then have an entry point out there. That entry point is going to call this script. That script is going to be a little fixed perm script here, and I look at that and I say I can only run that when I'm root. Because if I'm going to do a usermod command, I need root access to be able to run this. So the developer is going to start their container up as root. So that's now terrible. The sysadmins hate us. But then I run this exec command. I include a go-su in there. Go-su is a lot like an su command, but it also includes an exec. And in case you don't know about exec, it just says make the process I'm kicking off the new current process. So everything runs as PID1. Now when I do an exec, my new PID1 is whatever process was passed in. The little $@ sign there, that says whatever the value of command is, that is when I'm getting ready to run with my exec. So that becomes the new PID1. You don't see a shell script anymore after you go into the container and start up with this. So that all goes away. So our application is now running as the app user inside the container after we fix the permissions. The one last change we have to make is we need to update the Docker Compose file that says it needs a little root user in there. Once we've changed that, the production Compose file has none of that. So our operations people are very happy in production because they aren't running stuff as root. They don't have the volume mounts. They're not overriding commands, none of that crazy stuff. And the developers can use this same version when they're doing stuff they're not developing. If they're pulling down a lot of other images to play around with, they can still use the production version. So the end user here, just kind of recap that solution, is that the developers mount the code. It starts an entry point that runs as root. That entry point looks at the UID of the code directory, compares that to the UID of the app user. If they don't match, it modifies the app user on the fly. The container automatically updates itself to become the new ID of the developer on the machine. That means any reads and writes to that directory from the container or from the host are the same UID, and you don't see those permission issues anymore. All right? So there you go. I promised slides here. Anybody that missed that link in the beginning, there's a QR code that goes to the slide deck. There's a GitHub repo with a slide deck, and that little base image is also there with the GitHub repo. So thank you very much.